8.6 are volumes by disk and washer methods. Okay, we've already talked about them a little bit. We've used integration to evaluate areas of regions. Now we're going to explore ways that integration can be used to find volumes of solid formed by rotating a region about a given straight line. In today's lessons, we're strictly rotating about either the x-axis or the y-axis. We'll get fancy next week and rotate about other lines. But right now it's just x-axis or y-axis. If a region in a plane is revolved about a line, the resulting solid is called a solid of revolution. The line that you're revolving around is called the axis of revolution. The simplest such solid is a right circular cylinder or a disk. So which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. For example, consider region R here, bounded by the x-axis, y-axis, and x plus 3y equals 6. I think we graphed that exact line yesterday, if I'm not mistaken. Now imagine rotating this region about, in this case, the y-axis, 360 degrees. So if you take that triangle and you rotate it, you're going to get this cone over here. Okay, you're going to get this cone that has this radius of 6 and this height of 2. Okay, now, yes, we have a cone formula. So to find the volume of the cone, we could use the idea of the volume of the cone formula that you would have learned back middle school geometry, 1/3 pi r squared h, or it says it comes out to be 24 pi. But this is where disk method comes into play. So we're going to explore the idea of a strip sliced through the region revolved about the y-axis. Remember that x would represent the coordinate of some point P on the graph, and as such is also the length of our strip. When the strip is rotated or revolved around the y-axis, it forms a thin disk. So when you guys know like how I draw a line a lot. That's basically what I'm doing. That line is representing just a real thin rectangle. You take that rectangle, basically we're just take one slice out of the cone. One slice out of a cone is a circle. Okay, and so you're finding the area of this circle, and then we're integrating it, and we're accumulating those areas, that's going to be the volume of the cone. Okay, so that's the idea there. You guys know area of a circle is pi r squared, right? So notice here, pi, radius, well, they didn't give us they didn't use the equation or anything, but this radius here has a distance of x. We don't know what it is in terms of the equation, but it's a distance of x. So x squared, and then dy, because this one, similar to like what we did yesterday, sometimes will be in terms of x, sometimes will be in terms of y. Dy just represents what variable we're working with and the height of that circle or that disk. Okay, so let's look at example 1 here. Write the volume of the cone as an integral on the interval from 0 to 2, then find the volume of the cone. So this is kind of taking where they left off, which right here, right? Because remember, I said this is the idea of pi r squared. We're always going to be thinking about pi r squared, and then officially that dy represents the height of the circle. As we set up our volume, okay, from 0 to 2, okay, so when it was perpendicular to the x-axis, we worked in terms of x's, right? When it's perpendicular to the y-axis, we worked in terms of y's. You're going to notice the same thing here. Our circular slice, okay, or actually what I say here is when you rotate around the y-axis, you work in y's. If we rotate around the x-axis, we'll work in x's. We're rotating around the y-axis here, right? So we're working in y's. So you'll notice the interval they give on example 1 says 0 to 2 because what are you at on the y-axis? 0 to 2, okay? So they tell us to use 0 to 2. Now, you're basically always integrating a circle. So when we do disk method and washer method, there's always going to be a pi involved, right? There's always going to be a pi. The radius squared. Well, the radius right now, if you just look at that horizontal piece, up above it's listed as x, right? X squared dy. We're not going to use x squared though, because we need to be in, everything else is y's, y's, y's. What is x in terms of y? So go back up above. This distance is a length of x, but it's the distance from the y-axis over to this equation. What is that equation? Yeah, I had to find it myself. X plus 3y equals 6. So if you solve that for x, what is x? 6 minus 3y. So down below on number 1, where there's an x, what are we going to put in? Not a y. 6 minus 3y. So this is going to be the integral from 0 to 2 of, now, are you guys okay if I put the pi out front? Can we still do that? Now, later, whenever. Instead of x squared, it's going to be 6 minus 3y quantity squared dy. Okay. Now, if we're doing this one by hand, I may throw calculators on some of them, but we've got to know how to integrate, guys. What's going to be the suggestion here to integrate this? Foil it out first, because then you're just going to have 3 basic terms, yes? So if we foil this out, pi times the integral from 0 to 2 of, what you got?
12.
Check again. 6 times 6? 36. 6 times 3y is 18y. The other 6 times 3y is going to be 18y. Minus 36y. Minus 3y times minus 3y. Plus 9y squared dy. Okay. So, pi. Let's integrate. Integral of 36 is 36y minus integral of 36y plus integral of 9y squared 3y cubed. Okay. And then from here it's doing the math. Nice part here is 0 is our second number, isn't it? Again, I'm always going to remind you, always check. Don't just assume I can ignore 0. When I plug 0 in, is it going to give me 0? In this case, 0, 0, 0, it will. But don't ever just assume. So, 36 times 2 minus 18 times 4. Oh. Plus 3 times 8. And I guess I officially should say minus 0, but 24 pi. Now, I believe they said that up above somewhere, didn't they? Somewhere it said 24 pi up above, I thought.
Yeah. Volume. Yeah.
Okay. Yeah. Okay, guys. That's your basics. Okay? Now, let's look at the top of the next page. Okay. I've kind of already explained a lot of this, I think, but when finding volumes of a solid of revolution, it's important to focus on what happens to each individual slice or disc as it's rotated around a line instead of thinking about the total volume. A thin slice or strip can be horizontal or vertical. Yes. Thank you. The volume of a disc sliced vertically is V equals pi r squared W. where, okay, r is the radius of the disk, and w is the width of the disk. Okay, so in other words, we're still just talking about area of a circle. When we start talking about the width, it's a cylinder, right? So in order to do area of a cylinder, it's area of the circle times the height. So you've got area of the disk, which is the pi r squared times the width of the disk. Well, the width of the disk is represented as your dx or dy. And then down here, if you have a horizontal axis of rotation. Horizontal axis is like rotating about the x-axis, yes? They're generalizing for future lessons, but anytime you rotate about the x-axis or any horizontal, we're going to work in terms of x, which means your equation has x in it, your a and b are x, and it's dx. Anytime it's a vertical. So vertical axis, we know the y-axis to be vertical, yes? Anytime it's a vertical axis, you're going to work in terms of y, which means your equation's going to be solved in terms of y. It's going to be dy, and guess what? C and D represent y values. Okay? You want to test? Okay. There you go. You're welcome. Okay. Do we... Okay, well, we're going to start this. We may or may not get through it, right? Let's see what we can do. Set up and evaluate these integrals. Give the volume to solve by revolving the region about the x-axis. Okay. Y equals negative x plus 1. What is that? Straight line. Intersects at 1. Slope of negative 1, so rise 1, run 1. It's basically going to go through 1 on the x and 1 on the y, yes? I don't know why I drew it through there, but, you know. Okay. Now, the idea here is they specifically tell us to rotate about the x-axis. You will often see me draw a little arrow around whatever I'm rotating around. It's just, if nothing else, it's a visual cue. It's a visual reminder like, okay, it's an x-axis problem. Okay? Now, with that in mind, our equation was y equals negative x plus 1, right? Okay. We are rotating about the x-axis, which means your rectangle is perpendicular to the x-axis, right? Because it's going to rotate about the x-axis. That's where it's going. With that in mind, this is, this is a height of y, if you will, right? Notice, what do we already have this solved for? We already have it solved for y. So when we start talking about pi times the, what they use, r of x squared, and then dy, realize, what is my r of x going to be? Not dy, sorry, dx. R of x is just your equation here. When it butts right up to the x-axis, you're just using, it's that distance right there. Okay? So with that in mind, do we know enough to set up our integral? Okay. We're going to do what? We have to remember there's always going to be a pi, because these are circles we're creating, right? Radius squared. Well, that means I'm doing negative x plus 1 squared times the width of the circle, so that's the dx, from 0 to this one. Not the y one, but the x one. Okay? So we got a little basics. Yes, you're going to FOIL. So pi times the integral from 0 to 1 of x squared minus 2x plus 1 dx. and 1/3 x cubed minus x squared plus x evaluated from 0 to 1. Pi times 1/3 minus 1 plus 1 minus 0. Pi over 3. Sorry. I went through that quick because I knew my timing was about out. That was basic math, basic calculus at that point. I trust you guys can do that basic calculus. We will pick up on Monday. And I will figure out if we're going to make it. We got through 2 of the 3 pages, really, didn't we? However, we got the big pages left, so we'll see.